Nice to have Kevin Yang. Welcome to the seminar. So Kevin is an NSF postdoc at Berkeley. I guess he'll be at Harvard next year. And so he'll be talking about universality and well-posedness for a time-inhomogeneous KPZ equation. So welcome, Kevin, and please proceed.
All right. Well, thank you, Sundar, and thank you, everybody, for inviting me to speak. And I do apologize for being a little late. So hopefully I try not to go too over time. Yeah. So let me start by sort of telling you about this KPZ equation and a little history. So I guess maybe a lot of people in the audience already know this equation, but I think this is maybe a pretty good motivation for the problem that I want to consider. So I guess the physics that Carter, Parisi, and Zhang wanted to model in this 1986 paper was for the dynamics of a stochastic interface between a stable phase and a metastable phase. So for example, if you consider an Ising model where you have minuses above the x-axis and pluses below the x-axis, you can consider the Glauber dynamics with a zero temperature, basically, and a weak external field, which will favor one of the phases. And then if you sort of look at the evolution of the interface between the two phases, what you see is supposed to be sort of KPZ-like. So in terms of where this model comes from, there are a number of ways that are ultimately equivalent to each other to come up with the model. But one that I particularly like is to sort of assume that the local behavior of your stochastic interface fluctuation looks like a Gaussian free field. So in this talk, I'll stick to one dimension, though I guess heuristically or physically, you can think of any dimension. So what we'll do to come up with the model is to just take the Gaussian free field measure on the torus, and then to get a dynamical model, you can write down the corresponding Langevin dynamic, which is just this additive stochastic heat equation. So in particular, psi is the space-time by noise. But you know, this model, it's a dynamical one, but it's more for equilibrium interface because the model is reversed. So in the Ising context, it's like if you had no external field. And to write down a non-equilibrium interface model, one way to do this is to just add a first-order slope-dependent term, which sort of just tells you that the interface also evolves according to the local geometry. And you get this stochastic PD right here. But you know, if you give a general non-linearity f, this equation is very difficult to say anything about. So to write down a much simpler model, you can Taylor expand this f up to second order. And what you'll see is that the first two terms don't really tell you anything interesting besides this sort of space-time reference frame that you need to look at. And then the quadratic term is the first term that sort of tells you maybe something a little interesting with the actual physics. So this is the one that you keep. And then the model that you get at the end of the day is this stochastic PD at the bottom of the slide that we now call the KPZ equation. So there's sort of one question you can ask about this KPZ equation that's fairly natural because you're looking at fluctuations in some statistical mechanical model, which is a question of universality. So in particular, the construction of this KPZ equation that I gave is a really non-canonical one a priori, because you assume and you sort of choose the local behavior of the interface to look like a Gaussian free field or, you know, a Brownian bridge in one dimension. Okay. So here's a sort of natural question you can ask about the sort of universality of this KPZ equation, which is to take this sort of measure instead of Brownian bridge. So for example, if you took a quadratic potential U, you would just get the Gaussian free field again, but you would like to consider this thing for much more general potentials. And to say I guess to sort of state the universality question more precisely, you do the same thing. So you look at the Langevin dynamic for this measure, which now gives you in general a nonlinear stochastic PDE. And then to get the non-equilibrium interface model, you add a first order term to this equation. And in general, you know, in principle, you could add whatever first order term you want. It turns out to be convenient to add one of this form, so just the potential derivative value of the gradient, because it preserves this measure as an invariant measure. But otherwise, you know, in general, you could put whatever you want and, you know, the story should be the same. So the universality conjecture, if it were true, would say something along the lines of any meaningful notion of solution to this equation with the first order term should just be the solution to some KPZ equation with, constants in front of the terms that depend on the potential in some way. But the stochastic PDE is ill-posed. Same thing with the KPZ equation for the same reasons. So really what universality is saying is if you take some sort of regularization of this equation, you solve the regularized equation, and then you take the limit of the solutions as you remove the regularization, what you get should just be KPZ. So that's the general question, or the general claim that we'd like to be able to explain rigorously, and that's going to be one of the main points of this talk. I should say, if anybody has any questions or anything, you should feel free to just interrupt me whenever. Okay, so let me now give you what I mean by a regularized version of this equation. But I guess 2 points first. So I'm not going to look at this equation just yet. I'm going to look at its gradient, mostly out of just my own convenience for now. And the other thing is, by regularization, I'm really just going to be taking a discretization of this equation. Then you have an interpretation in terms of interacting particle systems, for example. So here's the regularized equation. So there's some scaling parameter that's set to the scale of the system n, and then we're going to discretize the torus to get a finite set, finite space. And then the discretized equation is just given by this stochastic differential equation here. So you have this Langevin part with a second order term and a noise term that runs at speed alpha s squared. And then you also have this first order term running at speed alpha sub a. But the s, just means symmetric and the a means asymmetric. Okay. And just to be totally clear, this btx term, these are just independent Brownian motions over the discrete torus that are, I guess, Brownian in time. Okay, so there are a couple of important things to know about this stochastic differential equation. And the first bullet point here is a little loaded, so let me just try to explain what it's saying more intuitively. So this gradient operator on the discrete torus is a one-dimensional curve, which means that if you want to look for invariant measures of this STE, you should really be looking for, a family of invariant measures that's parameterized by this kernel. And the kernel of the gradient operator, it's spanned by constant functions. And you can even sort of see that as long as you redefine the potential, the right-hand side is basically invariant under constant shifts of U. So what this is saying is that there's a one-parameter family of invariant measures. And for each constant function determining the invariant measure, the value of that constant is just the expectation of U with respect to that invariant measure. Okay. So that's sort of the abstract general stuff. And then the really nice thing about this Ginzburg-Landau model, which is just this SDE right here, is that these invariant measures are actually exactly, you can write them down exactly. And they have a pretty simple structure. They're product over the discrete torus, and then the one-dimensional marginals are basically given by this Gibbs measure with potential U, except you need to introduce this linear tilt to get the right expectation. Okay. And then the other point about this SDE is that for general potentials U, it's not known whether or not there's any integrability or integrable structure behind the SDE. So that's just to say that in this talk, I'm not going to really rely on any sort of integrable structure for the SDE. Okay. So the sort of point of main interest here is rescaling limits for this SDE as n goes to infinity. And in particular, sort of ones that correspond to interface fluctuations. But the first step maybe is to understand sort of the law of large numbers instead of just fluctuations for the scaling limit. And this, I guess, in the interacting particle systems literature, this is known as the hydrodynamic limit problem. So I'm going to take this choice of scaling for the coefficients alpha s and alpha a, which ends up giving you this equation. And the first thing that you can see is that the Laplacian, the discrete Laplacian, and the discrete gradient are scaled to 2 weakly. So that in particular, you expect that these terms will actually give you anything as n goes to infinity. And on the other hand, the first order term is scaled appropriately. So we expect that, whatever limit that U has to be a first order PDE. And this is exactly why this choice of coefficients is in the so-called hyperbolic scale. And the exact choice of coefficients, so for example, this exponent 3/4 is going to be explained on the next slide. But for now, you can just think of this as some type of hyperbolic scale. So if you want to compute this, hydrodynamic limit for U, there's sort of one main step, which is at least heuristically this homogenization step. So what's happening locally in the system is that, it's moving very fast if you look at smaller scales than just, lengths of order n. So just by ergodic theory, you should sort of be able to replace local statistics like this U prime statistic by sort of homogenized versions. So expectations with respect to these invariant measures, sort of local invariant measures, which gives you this sort of approximation. And then you just plug this approximation into the SDE, you more or less follow your nose, and you can conclude, at least heuristically, that the scaling limit for U should be given by the solution to some type of first order scalar conservation law with homogeneous flux. Okay. Of course, this is all heuristics, and there's the problem of making this rigorous. So this is a problem that many people in this audience are sort of very familiar with, but it's attracted attention for the past few decades. I would not say it's very close to being completely solved. And there are a number of different methods that sort of give you results of different strengths and different flavors. But a lot of these methods really depend on sort of strong assumptions on the potential, for example, like convexity. Though there is one method, which is the relative entropy method of Yau, which doesn't give you quite the whole hydrodynamic limit, but it gives you quite a bit. And it works for a very, very general class of potentials. And the way this relative entropy method works is you want to prove some sort of measure theoretic statement, more or less, of the hydrodynamic limit. So you want to look at the law of U at time t, and you want to compare it to not the invariant measures of the system, but sort of space-time inhomogeneous tilts of the invariant measure determined by the hydrodynamic limit itself. And you want to estimate the sort of measures in relative entropy, and you want this relative entropy to be little of the hydrodynamic or macroscopic scale n. So to prove this estimate, you require two assumptions. And the first is you just assume the estimate's true with the initial data with respect to some smooth profile U0 of x that serves as your initial data for the hydrodynamic limit. And then the job is to sort of propagate this estimate in time. And it turns out that the necessary ingredient for that is regularity of the U process at quote unquote macroscopic scales, which ultimately just means, at least morally, regularity of the hydrodynamic limit itself in space. So of course we're in the hyperbolic scale, which means that sort of regularity estimates for the hydrodynamic limit aren't global in time, and they sort of blow up at some finite macroscopic time. Which means that the Yau's method doesn't give you a full hydrodynamic limit, it gives you a hydrodynamic limit that's sort of local in time. But again, the upshot is that it sort of depends. It doesn't really depend on many assumptions on the potential at all. And conceptually, it also has the benefit that sort of it tells you how to get at least a partial hydrodynamic limit using basically only the notion of entropy, which is, I guess, favorable from the point of view of pure statistical mechanics. But yeah. Okay, so now I want to go to the fluctuation scale. So I want to go a little past the hydrodynamics. And this is where KPZ starts to show up. And it turns out that at the hyperbolic scale, if you want to see meaningful fluctuations, like KPZ fluctuations, you have to scale time by a factor of n. So this has the effect of choosing alpha s equals n and alpha a equals n to the 3/2. So under this scaling, the Laplacian and the noise term, so the sort of Langevin part of the dynamics, are scaled appropriately. So you do expect that these terms give you something as n goes to infinity. But now the first order term is scaled to be somewhat singular. So if U does have it does have a scaling limit sort of with this choice of scaling, it's maybe not so surprising that KPZ is sort of a candidate for the scaling limit. And I'm also going to allow the potential now to depend on time, so that the process is time inhomogeneous. And the motivation for this is to sort of write down a model that's in non-equilibrium and a different type of non-equilibrium as well. So for example, there was a paper of Chang and Yau which sort of looks at it, morally similar situation. Technically, the details are a little different. And then, one of the sort of effects, however, of choosing a time-dependent potential is that these, you lose all notion of invariant measures because the invariant measure was basically a functional of the potential. Now that invariant measure is changing depending on how your potential changes. Okay. So to see how KPZ shows up from this SDE, here's the following heuristic. So the first thing you have to do is you have to sort of assume, so take some ansatz that U is somehow fluctuating about zero in some sort of weak sense, analytically, I guess. And I guess the interpretation of this is that we're looking at fluctuations about a constant hydrodynamic limit. Otherwise, you would have to look at fluctuations about some hydrodynamic limit that, is solving a first order hyperbolic equation at a speed that's divergent because we're scaling everything by a factor of n to the 1/2. And this is generally a nasty object. So we're just going to assume that the hydrodynamic limit is constant. In any case, you can still run this sort of homogenization argument. The only difference now is that the measure for the homogenization expectation depends on time, just because it's a function of the potential. But once you do this, you can start Taylor expanding this thing in the density parameter, so the sigma parameter, UTX, up to second order. You can plug this expansion into the SDE, and then more or less follow your nose to at least heuristically conclude that the scaling limit for U should be the solution to this time-inhomogeneous stochastic Berger's equation. At least if you sort of, change the x coordinate by a characteristic shift. That depends on time. So that's how stochastic Berger shows up. And of course, you can sort of undo the gradient. You can make an equivalent claim about KPZ. So if you sort of look at an appropriate antiderivative of the U process, you get something that people call the height function in this literature. And then the claim in this world is that the height function has a scaling limit, which is given by this time-inhomogeneous KPZ equation. Okay. So that's the heuristic. And of course, you can ask about trying to make this derivation rigorous. And as far as I know, something that works in complete generality is sort of way out there. Maybe like too much to ask for at this point. But nevertheless, motivated by Yau's method, I think it's still maybe interesting to try to get a method that derives this KPZ equation rigorously for a general class of potentials under some sort of assumptions that are basically finer versions of Yau's assumptions. And that's basically the main result of this talk. So if you take this height function, which is this sort of antiderivative of the U process, then this does converge to the time-inhomogeneous KPZ equation, which still have yet to tell you how to solve, as long as you have some reasonable initial data and as long as the following assumptions are satisfied. So the first is that if you look at the relative entropy of the initial data of the U process with respect to the not the invariant measure, but sort of the homogenization measure at time equals 0 and sigma equals 0 because we're fluctuating about 0. You want this relative entropy to be a priori little low of n to the 3/4. Okay. So I should say that the sigma equals 0. I mean, the exact value of the sigma constant isn't important. Any fixed constant will do. Perhaps more interesting is maybe this exponent 3/4. So there has been previous work on looking at fluctuations of hyperbolic hydrodynamic limits. And in that case, the stochastic PDs that people get aren't actually stochastic PDs. They're actually deterministic transport equations. And then the relative entropy assumption that they take is basically something like this, but they assume that the relative entropy is this exponent is 1/2. So you can think of this 3/4 as the following. So, in this model, we're not purely hyperbolic. We still have a strong sort of diffusive reversible component to the equation. So we should be able to get something a little above 1/2. But because we're looking at scales that are still finer than the hydrodynamic scale, we probably want something a little less than 1. And it turns out that 3/4 is basically the exponent that works. So the second assumption is some a priori regularity estimate of the height function, which, on the nodes, it's just you're saying some sort of older 1/2 norm of the height function can grow at most polynomial, at least at most polynomially, for some sufficiently small but fixed and positive x. So there are two ways of interpreting this sort of regularity estimate. So if the height function really is close to a Brownian motion, which if it's like KPZ, it should be, then this estimate holds with exponentially high probability because we allow for this polynomial growth. So it's something that should be true with sort of very high probability. I guess more physically, you can think of this assumption as basically assuming this ansatz from before that U was fluctuating around 0, but maybe some more quantitative sense. And it's sort of mesoscopic because this is really only telling you something if you look at gradients of H on length scales above some fixed power of n. And in particular, it's sort of a tighter finer version of Yau's regularity assumption. You could try to prove this assumption is true instead of just taking it for granted, though it seems that it just requires a lot of extra work. So for example, you have to be really careful about the topologies in which you get estimates for the height function. But at least for now, we're very happy taking this assumption. And then the last assumption, a priori doesn't really look like something in Yau's method. But as I'll explain shortly, it kind of is. So we do need some regularity for the potential. This is maybe not so interesting. What's a little more interesting is the fact that we need this quadratic coefficient in the limiting KPZ equation to stay away from zero uniformly. And this doesn't really tell you anything about the particle system. It doesn't really help you analyze the particle system at all, or the SDE at all. It's more there for actually making sense of the time-inhomogeneous KPZ equation itself. But maybe I'll get to that on the next slide. And then maybe the most interesting part of this assumption is the convexity or second derivative type bound on the potential. So strictly speaking, we don't actually need this second derivative constraint. What we really need at the end of the day is if you look at the generator for the U process at time t, and you look at the log Sobolev inequality that it satisfies with respect to its extremal invariant measures, that log Sobolev constant should be not necessarily quadratic in the length scale of the system, but sufficiently close to quadratic. And for example, just by Bakary-Emery theory, that's implied by the second derivative constraint. So, assuming this convexity bound actually makes writing the paper a lot easier, but it is explained in the paper how we can get rid of this constraint sort of fairly easily. Okay. So you can think of this result as basically a fluctuation scale version of Yau's method, but for deriving the KPZ equation. But just to give it a little more grounded footing, let me give you just one immediate consequence of this result. So if you assume that the initial relative entropy is actually sufficiently small exponential polynomial in n, so just replace 3/4 by something like this. And you assume that the potential is independent of time, then you can actually show pretty easily that assumption 2 is true. So you don't have to sort of take it for granted. And the reason why this is true is because, as before, at an invariant measure, the estimate is true. I should say at an invariant measure, which sort of exists because you have a time independent potential. The regularity estimate is true with exponentially high probability, so with a large deviation scale. And then just by classical duality of relative entropy and large deviations, you can inherit that estimate in this case. And just to give this consequence a little more context, there was a paper by Diel, Kubinelli, and Perkowski some number of years ago, which basically proves this result. But they have to assume that the relative entropy is order of 1 instead of polynomial in n. And if you look at their work, as far as I could tell, you can't really push this O of 1 relative entropy down to anything beyond O of 1. Maybe you can get some logarithmic correction. You can't really go much past it. So this is in some sense an exponential scale of theta under that result. Okay, and I should say this, this upper bound of 1 over a bunch of 9s, this is not optimal. It's just, I can guarantee that it works. The sort of reason why I didn't try to optimize is because I couldn't get close to the exponent of 1/2 with just this sort of trivial argument, more or less. Yeah. Okay, so now maybe I should tell you how to actually solve this time-inhomogeneous KPZ equation. And maybe I won't try to spend too much time on this because it's more on the stochastic analytic side of things, but I'll say a word about it. So, with the time-homogeneous KPZ equation, one thing you can do is you can try to exponentiate the KPZ equation, which is, what people call the Kohlhoff transform. And this has the effect of linearizing the KPZ equation. So the exponential solves some linear stochastic PDE that you can more or less solve with basic stochastic calculus. The sort of interesting thing here that's happening because of the time-inhomogeneity, and you can just check this if you want, a piece of paper and a pencil on you, for example, is that you get this extra log non-linearity, which makes the solution theory of this thing quite a bit more interesting. So for example, if you have uniformly positive continuous initial data, then just because the map Z log Z is uniformly shifts away from 0 and infinity, you can get local well-posedness in time. But if you want global well-posedness, you need a priori estimates above and below for Z, so that the log is away from 0 to infinity. And it turns out that you can get such a priori estimates, so you do have global well-posedness in time, in a sense that allows you to make sense of the KPZ equation through this logarithmic equation. And then the only thing about beta t not being 0 is because beta t is 0, then you're sort of dividing by 0 here. And then you run into another set of issues. I guess in summary, this equation is well posed by the coordinates. And that's exactly how we're going to sort of think of solutions to this equation. Okay, so let me try to put at least the universality result into some more context. So I'm not going to go through this entire slide because there's a lot here, but I did want to give credit where credit is due as much as I can. But I'll say a few things. So if you think about the result that we're proving, we're sort of saying take a stochastic PDE and ill-post stochastic PDE, regularize it, solve it, and show that the sort of limit of the solutions as you remove the regularization is KPZ. So you can think of, analyzing the stochastic PDE using regularity structures. And there has been precedent. So in papers of higher collaborators, I can sort of tell you what they did. So let's go back to the beginning. Okay, so I guess one perspective you can have on these papers of higher and his collaborators is the following. So all the interesting stuff is happening in the singular, this first order. So instead of, sort of dealing with this equation and having to deal with this sort of nonlinear second order operator, just replace this thing with a Laplacian and sort of see what you can do. And in that case, in these papers, they're able to show that, meaningful notions of solution to this equation are just KPZ. But as soon as you change the second order operator into a Laplacian, you change the model basically entirely. And the reason why is because if you have a Laplacian here, instead of this sort of nonlinear operator, then this equation becomes more or less a perturbation of a Gaussian thing, which means that all these homogenized coefficients that show up in the limiting KPZ equation are given by Gaussian expectation. But, just by the result that I've given you, it's not true at all than Ginzburg-Landau. So for this second order operator, the homogenized coefficients are Gaussian expectations given by non-Gaussian expectations. But in any case, you can sort of ask yourself the question, what if we just sort of analyze this stochastic PDE regularity structures? Can you do something like this successfully? And the answer, at least at this point, seems to be no. And there seems to be a fairly strong obstruction to this, in that regularity structures really relies on sort of analytic regularity estimates for this second order operator. If you have a Laplacian, you have very strong regularity estimates. But in general, for these nonlinear operators,
Kevin?
Yeah.
May I ask you a question?
Yeah.
So, would you say that, in a sense, this type of equation you are looking at is in the language of PDE fully nonlinear, and that's why all this machinery of regularity structures doesn't work properly?
Yes, exactly.
And so it would be fair to say that in a sense, the particle systems are fully nonlinear, no?
Yes, so these particle systems are fully nonlinear. You can do sort of things where you take a symmetric exclusion process, for example, with constant symmetric part, and then you have a speed change in the asymmetric part. You might be able to say something about that. But there are sort of difficulties in that sort of regime in that type of world too, that you don't see, for example, in this problem.
No. Thank you.
Yeah, thank you. Yeah, and yeah, please keep the questions coming. In any case, as sort of Milton referred to or alluded to, the second order operator, you only have the Georgi-Nash-Moser estimates for this thing, which are far too weak to run the regularity structures argument. So, something has to be done here. Okay. I guess, okay, so there's a sort of another approach that you can take to this universality problem, which is this theory of energy solutions that people at this seminar know quite a bit about. So this theory of energy solutions, what it tries to do is it writes this KPZ equation, or with the gradient equation, stochastic Berger's equation, doesn't really matter, as a martingale problem. The sort of benefit here is that a lot of the particle systems and interface models we're interested in, they have a Markovian structure. These Markov processes and martingales are very compatible just by each other. So you don't see any of these structural obstructions, in principle, in energy solutions that you see in regularity. The sort of issue, however, and this is really the only downside to an otherwise very nice and very clean theory, is that to make any of the estimates work that sort of allow the Martingale problem to function and be well posed, at least for now, you need the process that you're working with to be stationary. And in particular, you need a notion of invariant measure, which, for example, doesn't happen in these time-inhomogeneous processes. And this is maybe a little bit of a curiosity, but I think it's quite interesting. It's sort of, if you can try to think about how to remove this stationarity assumption in energy solution theory, and if you sort of look at what regularity structures is doing, it's exactly telling you how to do something. So, there might be some way to combine the two, but I think that's sort of not known. Okay, and then there's also been, some precedent for looking at time-inhomogeneous processes that have some type of KPZ type flavor. And in particular, there was work within a year ago, actually, that looked at a discrete time set with time-inhomogeneous rates. I guess. Okay, so yeah, so now I want to give some idea of the proof of this universality result, and not give the full proof in details, but give you just some sort of ideas to what it feels like to prove this result. And I won't say much about the proof of the well-posedness result because it's just a PDE argument at the end of the day. There's no stochastic problem floating anywhere, and it really just amounts to maximum principles. So let me just sort of focus on the universality for now. So just by definition, what it means to solve this time-inhomogeneous KPZ equation. If you want to show the height function converges to that thing, what you have to show is that if you exponentiate the height function, you converge to this sort of exponentiated KPZ in place, Kohl-Hopf transform. So you can compute the stochastic PD that this microscopic Kohl-Hopf transform solves, the Z function solves. And you can isolate basically discretizations of every term that appears in the limiting stochastic PD that you're trying to derive. And of course, the equation doesn't just completely, just amount to that. You also have some error terms. And these error terms are in principle a priori order n. And these error terms take several lines to write down, which is why they might be down in the slide. But I think the most interesting part of this error term, what turns out to be the leading order part, is this Q statistic right there. So just briefly, this Q statistic, the first component to it, script U prime, this just comes from the script U prime that shows up in the H SPDE. This linear term in the Ginzburg-Landau SDE and this alpha U term, this sort of comes from just following this characteristic shift that you have to follow if you actually want to see interesting statistics. And then just playing around with the Kohl-Hopf transform gives you this funny factor. And this funny factor, it's not sort of a thing that shows up, it actually plays a very important. So if you look at the homogenized version of QT, and you think about it as a function of this sigma parameter, so this sort of density or expectation parameter in the measure. You can look at its sigma derivatives of degrees 0, 1, and 2. And if you evaluate these derivatives at sigma equals 0, which is the thing that we're fluctuating about a priori, you get 0. So what this is telling you is somehow that, if you believe the KPZ heuristic from before, the asymptotic contribution of this thing should vanish as m goes to infinity. And this is the entire starting point of this of proving universality through this Kohl-Hopf transform. And maybe in a little more detail at this point is somehow the Kohl-Hopf transform knows how to introduce this sort of correction to your nonlinearity. And just to get a handle on what this thing is, if U is a Gaussian potential, which is basically the model for what happens with the KPZ equation itself, this is just the second Hermite polynomial, which is the thing that shows up when you try to use Kohl-Hopf for the KPZ equation. So the point here is somehow the Kohl-Hopf transform knows how to sort of quadratically correct, quote unquote, any general nonlinearities. So the form of this correction is maybe model dependent, but the fact that it exists should be modeled to be a sort of universal thing. And everything that I've said so far, it's an algebraic calculation. Everything's exact. And the point of the Yau type assumptions is just proving the statement that the effective behavior of QT vanishes. And now here to give you a bit of a subtlety, but I think it's an interesting one, especially if you sort of think about these things quite a bit. So again, this Kohlhoff transform is telling you that it can sort of make sense of basically any nonlinearity, any sort of the nonlinearity for any choice of potential. If you think about what the energy solution theory is doing, it's sort of taking your nonlinearity, this replacing it by a quadratic, and then you're left with making sense of the quadratic thing sort of on your own. And that turns out to be sort of the hard part, I think, at the end of the day. Is, you know, one of the lessons that sort of learned in doing this. But in any case, let me sort of give you some ideas to why the effective contribution of QT vanishes. And you know, what I mean by this is you have to multiply QT by n, so you need sort of estimates on this thing of little of 1 over n. And it's not just multiplying by n, you also need to multiply by the ZTX. And this introduces problems for the following 2 reasons. So you can think about the ZTX term as this sort of Kohlhoff transform term as just a test function. Right? So you can think of it sort of in purely analytic terms. The problem when you do something like this is that the regularity of ZTX is pretty horrible as far as test functions go. So if you just try to treat this thing as a test function, sort of estimates, error estimates that you get, certain terms that you get, you sort of can't control them in the way that you want. Sort of second way you can view the ZTX term is as just a random functional system. And then you can try to do this sort of homogenization stuff, like this type of stuff, for the product of Q with that ZT term. The Kohlhoff transform is a highly non-local thing. It's a highly non-local functional of the system. And this homogenization stuff only really works for local statistics because it really requires the process equilibrating on local scales very quickly. So you have the obstruction there. And what ultimately saves you is the fact that the evolution of the Z term is available. So it's sort of that particular fact. And it's not just that, you also need to sort of know exactly what the ZT term is sort of as a functional system. I guess the ultimate point there is that the Z factor doesn't actually make the problem impossible. You can still sort of think about it. Okay, so in any case, let me sort of just give you an idea as to how this or why this QT term sort of has a vanishing contribution as n goes to infinity. So the general sort of strategy is actually not new to the interacting particle systems literature. And it goes by the sort of homogenization plus Taylor. So as an heuristic, you want to replace QT by its homogenized version, except you want the density parameter to not just be UT of x, you want it to be a mollification of UTX on some length scale that's just above n to the 3/4. And the reason for this is just you can sort of estimate this homogenized version directly by Taylor expanding in the density parameter, this UTX alpha, which tells you that because the first d equals 0, 1, and 2 derivatives vanish, this thing is basically cubic in its multiplication of UT of x. And now you just use your regularity estimates to sort of show that this thing is little o 1 over n. So you can, and to justify this replacement of QT by this homogenized version, it turns out to be much more fruitful to do something that seems a lot more complicated, which is to first replace QT by a homogenized version on some length scale L1, and then which is of order 1, and then interpolate between L1 and this Ln term just by doubling the length scale iteratively. So I should clarify again that this general strategy isn't new. You can find it, I think, in the Chang Now paper, where they look at fluctuations of Ginzburg-Landau in the reversible case. But it is a very important part of this energy solution theory as well. And again, I really haven't said anything analytic. I've basically just made algebraic and exact statements only, except for this Taylor expansion estimate. So really, the money is made by justifying this sort of replacement in the length scale for this dyadic scheme. Okay, so to justify this replacement, just take the difference between the homogenized QT functionals on neighboring length scales. Excuse me. And the first sort of crucial observation is that this term is quote unquote fluctuating. So if you look at its expectation with respect to any time t homogenization measure, for any sigma, you get 0. And this, more or less just followed by the tau property for conditional application. It's not too hard to see. So again, this thing is a fluctuating thing, this difference. So to get estimates for it, sort of schematic that you want to, I guess, the thing you want to do is you want to take its space-time averages and sort of exploit the fact that fluctuating things give you square root cancellation when you average them. So let's average this thing on timescale tau j and on a block length j. And there's this inequality, which is known as the Kipnis-Farr anomaly, which basically tells you that, when you average in time, you get square root cancellations. And then just sort of by mixing properties of the homogenization measure, when you average in space, you should also get square root cancellation. The only sort of subtlety that I want to emphasize for now is that these square root cancellations should have factors that a priori blow up on the length scale algorithms for exactly these two factors. And the reason for this is, heuristically, when you average in time, the way you get square root cancellations is because the system is sort of equilibrating or relaxing on the support of your function. But if the support of your functional is increasing, then this becomes a harder and harder task for the particle system to do. So the sort of square root cancellation should deteriorate in the length scale, which is where this Lj factor. And then as for spatial averaging, it gets Lj to the 1/2 basically for the following reason. If you take some support length Lj term and you sort of average its, spatial translates, its support is going to overlap with Lj many other shifts. So you lose this sort of orthogonality as Lj moves higher in scale, and just like Cauchy-Schwarz, for example, you get this Lj to the 1/2. So in principle, something is deteriorating as the length scale gets higher and higher, which maybe makes a little sense intuitively. But the sort of thing that saves you at the end of the day is that, as the relaxation estimates get worse and worse, your a priori estimates for Q get better and better, just by this Taylor expansion argument that sort of deteriorates the length. So this is in particular why the sort of interpolation procedure is, useful, because, as the homogenization gets harder, your a priori estimates get better, and they somehow cancel each other out at the end of the day. And so in particular, if you choose tau j and lambda j appropriately, but independently of the length scale j that you're sort of modifying on, you can play. Okay, so I'll also emphasize that this type of estimate, though maybe not in this sort of exact writing of it, and maybe with these exact terms, this type of estimate, this type of procedure is also known to the literature. And in particular, it's a very important part of the energy theory, this sort of interpolation scheme. And in particular, the reason why I justified it being important, this interpolation, was also known to the energy theory. And now here comes sort of the new one. But so to take advantage of these, square root cancellations in time, you need the Kipnis-Farr inequality in general. But this Kipnis-Farr inequality requires your process to be sufficiently close to being a stationary process. And this is, for example, why the energy solution theory is restricted to stationary processes for now. So, one of the main goals of this talk is to somehow, avoid that. Okay. So here's sort of the first crucial observation. The scales that you need to time average and space average on, and the scale of the multiplication, are both sort of mesoscopic local scale. And the system, is relaxing to invariant measure should be relaxing very quickly on local scales. So at least intuitively, you should believe maybe that the system is sufficiently close to being a stationary process on local scales, which is really all you need to get this estimate to work. And there are two ingredients to proving something like this. So the first is that if you look at the system at any time t, then in some sufficiently strong sense, it should be pretty close to, or the law of the system at time t locally should be pretty close to one of these homogenization measures. And then you can know, if this were true, you could just replace the law of the system with the homogenization measure. Done. This turns out to not be the case, because the scales that you need to replace the law of the system on, and the scales they need to average on are just sort of too big for that naive replacement to work. And the sort of resolution to this is a local to global type argument, which takes smaller scale estimates that are easier to get because you can replace by local equilibrium on those scales and sort of glue them into larger scales. And because of the audience, maybe I'll just say a word about this instead of just skip it entirely. So if you look at if you let a tau lambda just be the average of this fluctuating thing on the space-time block 0 tau times lambda, the first step is to look at a sufficiently small tau 1 and lambda 1 scale. And then just use the fact that basically the average is controlled by the L infinity form. So you can just introduce for free this a priori estimate for tau 1 lambda 1 average given by the L infinity number T. And then you can actually also introduce the sort of benefit from spatial averaging, because the spatial averaging doesn't require Kidney's bar. It actually is true with exponentially high probability with respect to the homogenization measure. So you can basically introduce this for free if you work with it. So you have these sort of small scale averages and they have a priori estimates. The next step, in step 2, is to sort of glue these smaller scale averages onto slightly bigger scales, tau 2 lambda 2, while retaining the same a priori estimate. Of course, there are some error terms that you need to address in this step, though they turn out to not be that big of a deal. So now you have a slightly larger scale average with the same a priori estimate, and then the third step is to replace or improve the a priori estimate from lambda 1j to lambda 2j. Where lambda 2j satisfies 2 constraints, it's a slight polynomial improvement over lambda 1j, and it's a little suboptimal to compare to what the square root cancellation heuristics should be the case. So to control this error term, you can try to take its first moment with respect to these homogenization measures at time t. And because this lambda 2j a priori estimate is suboptimal compared to what square root cancellations imply, this sort of first moment with respect to the homogenization measure is not a big deal. This is sort of control. And then you need to pay the cost of sort of reducing your system from or to these local homogenization measures, and this cost ends up being not a big deal. And then the fourth step is to iterate. So what's happening is you have a slightly larger scale average with a slightly improved a priori estimate. Now you increase the scale of the averaging of it all, and then increase the or improve the a priori estimate, and then you just iterate order one number of times until you get the a priori estimate that you like. And the main reason why the strategy works is because the main difficulty is when you try to replace or reduce the local homogenization measures on larger and larger scales. But the cost of doing so is always sort of suppressed by the a priori estimate that you get, which improves as the scale goes up. So again, there's sort of two competing factors happen to sort of magically cancel out, which is why this strategy. Okay, so what we said now is somehow that if you look at any time t, the law of the system locally should be very close to one of these homogenization measures. But this isn't quite enough to make Kintner-Varadon work. What you also need is that the process itself is sufficiently close to stationary on the scale. So one thing that you can imagine trying to do is just use Gersana to freeze the time dependence of the potential locally, and just pretend like you have a time-inhomogeneous process, and sort of work with that thing and be done. Except the cost it turns out to freeze the time dependence of the potential ends up being too big, so you can't sort of control that, unfortunately. So the sort of remedy to that is you go back to the proof of the Kipnis-Varadon inequality. You sort of see exactly what you do. And it turns out, I guess because of time, I won't really explain the details of this, but it turns out that all you really need for the Kipnis-Varadon inequality to work is some estimates for the Kolmogorov equation associated to a local version of the U process. And in particular, what you need are sort of just, pointwise and gradient and energy estimates for this thing. Which in particular means that this problem is completely addressed by PDE. So there's no sort of probability happening. Okay. So let me sort of conclude with just sort of a couple of things that one can do sort of beyond this work. So one thing you can try to obviously do is remove the Yau type assumptions. If you want to remove the regularity estimate assumption, just sort of, it seems like you can just sort of do the same thing, except to be be even more careful about the topologies that you're getting estimates in, which seems to be quite a bit of work. The other thing you could try to do is remove the relative entropy assumption, which maybe you can do along the following lines by using sort of the smoothing property in relative entropy, the associated Kolmogorov equation. I don't really have anything rigorous to say in that direction as of now. And then the other thing you try to do is sort of look at, scaling limits for interfaces that are not exactly KPZ, but KPZ perturbed by sort of effects like lattice effects. For example, if you include this cosine term in the Hamiltonian, include a wedding and thinning transition. But maybe for the sake of time, I'll sort of just stop there if anybody has any questions. Yeah. No problem with that. Yeah. Thank you.
All right. Well, thanks very much, Kevin, for a very nice, interesting talk. Could I open the floor for any questions?
All right, maybe I should say I should plug my computer in really quickly, but I'm sort of listening still to that.
Okay, no problem. No problem. Take your time. I guess I could start it off a little bit.
Yeah.
So the initial condition, even in the stationary case, you're taking it so that with respect to the invariant measure is order n to a small power. Is that right? It's,
yeah. So if you want the result that doesn't require an arbitrary regularity estimate, then yeah, it's n to some small power.
And so in the Chang and Yao paper, for instance, it's you can get a macroscopic interval, right? So with this, this would allow you to change a mesoscopic interval, I guess. Is that right?
Yeah. So the Chang and Yao paper, they don't really have any assumption on the initial relative entropy. They have this order n thing, which basically comes for free.
And should one try for that, or you were saying something with n to the 1/2, or maybe there's something in the scaling that I didn't quite get.
Oh, so the truth should be that you shouldn't need any relative entropy assumption. I think you shouldn't need one to get KPZ. If you look at Chang and Yao's work, well, first of all, there's no singular stochastic PDE stuff in there, which is one of the reasons why they can allow for order n. The other thing somehow is that they also prove these sort of C1/2 regularity estimates in their paper. But if you try to use their argument, you have to deal with this sort of singular first order term in the SPD in this equation. And it turns out that the sort of scaling for that thing, it might look sort of weaker than the scaling for the symmetric part, but you really that presents a lot of issues. That, for example, if energy solution theory worked out, even without the stationarity assumption, that would still pose a problem. So it's really this first order thing that it affects the limiting stochastic PDE, and it also affects the sort of technical estimates that change it down.
And you're working on the full line or on the torus? I just.
I'm working on the torus, but the full line shouldn't be that big of an issue. You just have to sort of localize.
Right. Okay. Well, I might have another, but anybody else with a question?
Quick question. A little bit technical. So it's just that when you look at Ginzburg-Landau, there are various. It's very nice because you have various tools available. Like, for example, all these things about diffusion. For example, log Sobolev gives you a lot of information, right? Because it gives you immediately regularity of densities and things like that. It's so. I just wondering how much you really need about all this nice stuff for these things to work.
I guess the only thing that you need for log Sobolev is just the entropy inequality, right? So when you use the entropy inequality, you need to control the entropy. You control the entropy. The only way I know how to effectively control the entropy that sort of takes advantage of the fast-moving properties of the system is using a log Sobolev inequality and the Euclid form for entropy reduction.
Okay.
So that's the first thing. The second thing that you need, for example, that you can get if you have a convex potential, but it should be true for any log symbol with long potential. So that if you look at the speed of propagation of the system in space, this thing should be diffusive with the drift of order 10 to the 3 times. If you have a convex potential, you can basically just prove this because linearizations of the SPD become parabolic. So you have
Yeah.
but there's work of Davies and stuff that shows that all you do is this log bubble.
Okay.
Other than that, everything else you could just replace. You could replace the log suburban inequality with spectrum gap as in energy.
Okay. Yeah. Thank you.
Yep.
Anybody else with a question or comment? Well, maybe I could ask you later on. So if there are no further questions, why don't we thank the speaker again, and I guess we can close the seminar and then talk next week.
Thank you.
Thanks, Kevin.
Yeah, thank you.
Thank you, Kevin.